In this video, we are going to talk about the periodic trends in atomic radius. Let's start with the definition of atomic radius. If the atoms were in sphere shape like bullet boards, it would be easy to measure the atomic radius, right? Because they would have fixed and defined radius. However, we know based on the quantum mechanical model, their shapes and boundaries are much less definite than sphere. There's a nucleus and there's an electron cloud around the nucleus of an atom where electrons are most likely to be. So we cannot talk about real, clear, defined boundary of the atoms, and it's difficult to define the radius. So scientists found different ways to define atomic radius based on the distance between the atoms in various situations. On the right side of the screen, we have a collection of krypton atoms. When two of these atoms collide with each other, they bounce back like colliding billiard balls. This bouncing back happens because the electron clouds of the colliding atoms cannot penetrate each other. For this reason, the shortest distance separating the two nuclei during such collisions is twice the radii of the atoms. We call this radius the non-bonding atomic radius. On the other hand, an attractive interaction exists between any two adjacent atoms in the molecule, and it leads to a chemical bonding between the atoms. This attractive interaction brings the two atoms closer together than they would be in a non-bonding collision where the atoms bounce back. So we can define an atomic radius based on the distance separating the nuclei when the two atoms are bonded to each other, as you see in the example of bromine molecule. The bonding atomic radius, also called as the covalent radius, for any atom in a molecule is equal to half of the nucleus to nucleus distance. As you see in the image, the bonding atomic radius is shorter than the non-bonding atomic radius. And generally, when people speak of the size of the atom, they mean bonding atomic radius unless otherwise noted. Before we move forward and talk about the periodic trends in atomic radius, we need to talk about another concept, which is effective nuclear charge. So, if you recall the Coulomb's law, opposite charges attract each other and like charges repel each other. Also, Coulomb's law states that the strength of the interaction between two electrical charges depends on the magnitudes of the charges and the distance between them. Let's examine the atomic model in the light of the Coulomb's law. In an atom with one electron, the nucleus is positively charged and the electron is negatively charged. So the nucleus pulls the electron in closer, and we can say that electron experiences the full charge of the positive nucleus. However, in an atom with many electrons, as you see in the figure, each electron is simultaneously attracted to the nucleus and repelled by the other electrons. So the inner electrons partially screen outer electrons from the attraction of the nucleus. Sometimes this is called shielding effect. So the outer electrons do not experience the full nuclear charge. So scientists created another term, which is the effective nuclear charge, to calculate the net positive charge experienced by an electron. So there is a formula that we can use for the effective nuclear charge calculations. The formula says effective nuclear charge is equal to actual nuclear charge minus screening constant. Then what is actual nuclear charge? Actual nuclear charge is equal to the number of protons in the nucleus. And also, if you recall, the atomic number is also equal to the number of protons in the nucleus. And the screening constant is the number of core electrons in an atom. Let's try to find out the effective nuclear charge of this outer electron experienced. We need to know actual nuclear charge and the screening constant. As you see, it has 9 protons, so it means that its atomic number and its actual nuclear charge is 9. And also, we have 2 electrons in the inner shell, so the screening constant is approximately 2. If we plug these numbers into the equation, 9 minus 2 is equal to plus 7. So what is this number? This number tells us the nucleus pulls the outer electrons closer with a charge of plus 7. As a second example, we have an atom with 4 protons in the nucleus. So its nuclear charge is 4. And since it has 2 electrons in the inner shell, its screening constant is 2. From the equation, 4 minus 2 is equal to plus 2, so we have plus 2 as an effective nuclear charge. Again, it means the nucleus pulls the outer electrons with a charge of plus 2. These numbers shows us how strongly the outermost electrons are pulled by the nucleus. We can say that the greater the effective nuclear charge, the more strongly the outermost electrons are attracted to the nucleus. Now you have enough knowledge to examine periodic trends in atomic radius. We are going to start with a trend within the groups. As an example, let's examine the atomic radii of the elements in the first group. You see the first 4 elements from the group 1 to compare their atomic radii. The first thing you should do is drawing their electron configuration. At this point, if you don't know how to draw an electron configuration of an atom, it is a good idea to go over that before you go ahead. For each element, you should check the periodic table to find out their atomic number. So, atomic number of hydrogen is 1. It means that it has 1 proton in the nucleus. And we know that in a neutral atom, the number of protons equals the number of electrons. So, it has 1 electron in the first energy level. We'll have just a simple version of an atomic model, but right now it works for us. We have lithium, which has 3 protons in the nucleus and then 3 electrons. So we put 2 electrons to the first energy level and then 1 electron to the second energy level. So similarly, we have electron configuration of sodium and potassium. Based on these electron configurations, do you think atomic radii of the elements increase or decrease as you go down within a group? As we see, hydrogen has 1 energy level, lithium has 2, sodium has 3, and potassium has 4 energy levels. So as we go down, the number of energy levels increases within a group. So atoms become larger and larger, and the atomic radius increases from top to the bottom within a group. So, we can say that within each group, atomic radius tends to increase from top to bottom. This trend results primarily from the increase in the number of energy levels. We have a question here, and it asks us to compare the size of the beryllium and calcium. I want to note that when they ask us to compare the size of the atoms, they generally talk about the atomic radius. So it means that we need to compare their atomic radii. Again, start with the electron configuration. To do that, check the periodic table to find out their atomic numbers. We have beryllium, which has 4 protons, and so 4 electrons. And we have calcium, which has 20 protons and 20 electrons. Their electron configurations look like these. You will realize they both have 2 valence electrons, so they are located in the second group. As you see, while beryllium has 2 energy levels, calcium has 3 energy levels. So since calcium has 1 more energy level, which is farther away from the nucleus, the atomic radius of calcium is bigger than beryllium. Now let's see how the atomic radius changes in periods. It's a little bit complicated than the groups, so it's okay to be confused at first. As an example, I picked lithium and fluorine elements to examine how the atomic radius changes in second period. We start with the electron configurations of lithium and fluorine atoms. Since they are in the same period, they have the same number of energy levels. Then we understand that the energy levels doesn't give us a clue about the atomic radius change across the period. So we should consider their effective nuclear charge to find out which atom is bigger. As we talk about effective nuclear charge, we use the formula to calculate lithium's and fluorine's effective nuclear charges. The lithium's effective nuclear charge is +1 and fluorine's effective nuclear charge is +7. It means that the nucleus of fluorine attracts the electrons more strongly, so the atomic radius of fluorine is smaller than lithium. If we think about all the elements in the same period, they have same number of energy levels, but their proton numbers increase from left to right across a period. It means that their effective nuclear charge also increases, and their nucleus pulls the electrons more strongly, and atomic radius gets smaller and smaller across a period. To summarize, the atomic radius of atoms generally decreases from left to right across a period, and the atomic radius of atoms generally increases from top to bottom within a group. So in this image you can see how the atomic radii of the elements look like relatively. So we have another question which asks us to arrange oxygen, chlorine, and magnesium in order of increasing atomic radius. After checking the electron configuration of these three atoms, we see that oxygen has 2 energy levels and magnesium and chlorine have 3 energy levels. So we can say that oxygen should be the smallest one. Then we need to decide the bigger one between magnesium and chlorine. Since they have same number of energy levels, we should check their effective nuclear charges. Magnesium's effective nuclear charge is +2 and chlorine's effective nuclear charge is +7. So since chlorine's outermost electrons pulled more strongly by the nucleus, its atomic radius smaller than the magnesium's atomic radius. So increasing order should be oxygen, chlorine, and magnesium. I hope this video helped you to understand the periodic trends in atomic radius. Stay tuned for the periodic trends in ionization energy. Thank you.